All right, let's dive into a classic physics puzzle. Seriously, this thing looks simple, but the answer is so counterintuitive, it has tripped up students for decades. And the solution? Well, it all comes down to one of the most important rules in all of physics. Our challenge today comes from a book that is, let's just say, legendary among physics students, i.e., Irodov's Problems in General Physics. We're tackling problem 1.156. If you've ever battled through a mechanics course, you know that seeing this book means you're in for a real workout for your brain. So here's the setup. You've got two guys standing on a buggy that's not moving. They want to get the buggy going as fast as possible, just by jumping off the back of it. The big question is, does the timing matter? Do they get a faster buggy if they jump off at the exact same time, or if one jumps and then the other? What does your gut tell you? To solve this, we can't just go with our gut feeling. We need a tool, a fundamental principle. You know, for anything in physics involving things pushing off each other or exploding or colliding, there is one golden rule you always turn to. And that rule is the law of conservation of momentum. Now, the textbook definition says that for any system with no net external forces, the total momentum before an event has to equal the total momentum after. Basically, in a closed system, the universe doesn't let you just create or destroy oomph out of nowhere. It all boils down to this beautifully simple equation. The total momentum you start with has to equal the total momentum you end with. This simple idea of balance is going to be the key that unlocks this entire problem. So let's just double check. Can we actually use this law here? Well, first, we define our system. That's the buggy plus the two men, everything involved. Next, and this is super important, the problem tells us that friction is negligible. That's our green light, because friction would have been an external force messing things up. Since there are no other outside forces pushing or pulling horizontally, our system is isolated. That means conservation of momentum isn't just a good idea, it's the law. Okay, let's get to it. We'll start with the first scenario, what I like to call the team jump, where both guys leap off at the exact same time. Let's break this down. Before they jump, nothing's moving, so our initial momentum is just a big fat zero. Easy. Now, after they jump, the buggy scoots forward with some velocity we'll call v1. But here's the part we've got to be careful. It's a classic mistake. Their jump speed, u, is measured relative to the buggy. So for someone watching from the ground, the men's actual speed is their jump speed plus the speed of the buggy they just jumped from. That's why their velocity is u plus v1. So our equation is pretty straightforward. 0 on one side and the buggy's momentum plus the two men's momentum on the other. You just do a little bit of algebra to solve for v1, and this is what you get. That's the buggy's final velocity for case 1. And that little negative sign, that just tells us the buggy moves in the opposite direction of the men's jump, which, yeah, makes perfect sense. Okay, let's put this result on the shelf for a minute and check out case 2. All right, on to scenario number 2, the staggered jump. One man goes, then the other. Now, this is where things get a bit more subtle, and it's where a really common trap is hiding. This is it. This is the whole enchilada right here. When that second man goes to jump, the buggy is not at rest anymore. It's already moving from the first guy's jump. Forgetting this one little detail is the number one way to get this problem wrong. It totally changes the starting conditions for the second jump. So, since this happens in 2 steps, we have to solve it in 2 steps. We're going to apply our conservation law once for the first jumper, and then we're going to do it all over again for the second. Let's start with event 1. Okay, for the first jump, our initial momentum is still 0, but this time, only one guy with mass m jumps off. The buggy and the second guy who's still on it recoil together. We'll call their temporary speed v prime. We set up the same kind of equation as before, and we solve for v prime. This gives us the speed of the buggy right after the first jump, but before the second one. Now for the main event. The second man is about to jump. But remember, he and the buggy are already gliding along at that speed v prime we just found. This is our new initial state. We're starting with a system that's already in motion. So for this second part, our initial momentum is not 0. It's the momentum of the buggy and the second man moving together. After he jumps, the buggy's all alone and reaches its final velocity, v2. So we set the initial momentum equal to the final momentum, we plug in that expression for v prime we found a second ago, and we solve for our grand finale velocity, v2. And voila, here's our result for case 2. The algebra is a little bit messier, I'll give you that. But you can see right away, this formula for V2 looks totally different from the one we got for V1. So, the hard work is done. We've got our final velocity for the team jump and our final velocity for the staggered jump. The moment of truth has arrived. Let's put them side by side and figure out which way is better. Okay, on the left, we have V1 from the simultaneous jump. On the right, V2 from the staggered jump. Now, just looking at these two crazy-looking formulas, it's probably not obvious which one represents a bigger speed. So I'm asking you again, now that you've seen all the physics, which method gives that buggy the biggest final speed? Is it the team jump or the staggered jump? And the answer is the staggered jump. I know, it's surprising. Most people's intuition screams that they should jump together for one big push, but the math doesn't lie. It turns out that for any values of mass you plug in, the speed you get from jumping one by one is always, always greater. If you're more of a visual person, here you go. The final speed from the staggered jump, V2, is just plain bigger than the speed from the simultaneous jump, V1. No question about it. But the real question is, why does this happen? The reason is actually pretty cool. Think about it. The first guy jumps and gives the buggy some speed. Now, the second guy gets to push off from a platform that's already moving away from the direction he's jumping. It's like he gets to leverage that existing motion. He's able to impart an extra little kick of momentum to the buggy that he just couldn't have if it was standing still. In the original problem actually asks, how many times greater? Well, if you divide V2 by V1, you get this exact factor. And since the masses m and m have to be positive, this factor is always going to be greater than 1. And that leads to a final thought. This isn't just some weird little problem about buggies. This principle, the idea that you get a bigger boost by pushing off something that's already moving, is the exact same reason we use multi-stage rockets to get into orbit. Each stage pushes off the previous one, using its motion to get an extra kick. It really makes you think, where else do little details like timing lead to these huge, unexpected differences?